Destruction of police property.
Okay, I need to change. I need to get out of this. That was what I wanted to do before because I.
Okay, I muted everybody, so if you want to talk, you have to unmute yourself because there's a lot of background noise.
Okay.
Okay. So getting started here.
They're not expected, but they're not expected until tomorrow.
I'm not hearing it.
Hello.
Hello.
Get rid of this.
Okay. So can everybody see the screen?
Well, then we'll just use there.
Right.
Okay, yeah.
Yes, we can.
Yep.
I can see
Okay.
it.
Okay, awesome. Okay.
Very well.
Well, I'm going to get started here. I'm going to go into basically presentation mode. If people can't see anything, let me know, and I'll try to move stuff around. Okay, so this is the March 2021 edition of the PAS General Meeting. Welcome, everybody. So we're going to go ahead and get started. Let's see. Okay, yeah, I always forget which button I have to press. Okay, so this is the team for this year, and we're just going to go ahead and go through any updates people have. So, Mike, do you have anything you want to say?
Oh, not a lot, other than we had a good in-town star party with the UM Barry. And I have been up to the site. Everything was working. It might have been the last meeting, for the last meeting when I went, but I was up there. Everything was working great. The heater worked, the AC works, all the water works. The only thing is the trees are too tall, but we still saw a lot.
Yeah, there's been a lot of discussion about how to manage those. Maybe we can talk about that at the end if people are interested.
We need a presenter for next month. Yeah, so there's that.
Okay, so there's a
I've had
call
my-
out for a presentation for next month. So if people have ideas or have a presentation in their back pocket, please let Mike know and he can get you on the schedule. Okay, is Kent on? Anything on the times or? Nope. Okay. I don't know if John's on. Sometimes he's not on. If you're on, John, you can give us an update on the current membership. See, I can't see everybody in this particular view I'm in. Can't see who's on. Okay. And Jeff, you said you had a couple updates.
Yeah, I got a few things to share with y'all. Mike had just mentioned, we talked about, sorry, dog barking, trees up at the SPMOS. I went up there a day or two after the meeting just to lay eyes on things and talk to Walt. We had a member that volunteered to take his machine up there last month, if y'all recall, but he didn't have transportation for it. So I spent some time looking for that and kind of struck out. He lives a little ways away. He lives over north of Bay St. Louis. So it's a pretty good truck and haul from there up to our site. And especially considering the size of the machine that he had, I wasn't able to work anything out on that. But I had mentioned to you previously that my son-in-law does have a small excavator, and we did try to get him up there last weekend. It just didn't work out because of weather and some issues with some of his work schedule that he has going on. But right now we're going to try to get up there on April 10th or April 11th. That's the Saturday and Sunday after Easter. So we're going to give that a go. Right now, that's the plan. On the website, I also mentioned I'm looking for some help to do some updates to it. I reached out to a gentleman that runs a company in Slidell. He spent some time looking at the format, and he didn't think he could handle it. So in a way, it makes me feel better because I was scratching my head at the format of it. It's a little more involved. Most websites nowadays are made from WordPress software, and this is not that. It's all old HTML code, and so I'm not giving up yet. I'm going to look for another source. I have a statement of work together, so it'd just be a matter of shooting that statement of work off to somebody else, and we'll see what we can come up with. And one other thing, I've been, through our website, someone has reached out to us looking for someone to do a presentation with a group of kids on April 17th over in Metairie. I shared some of that by email. I think I CC'd Phil on that and was looking for some information. But what it is, it's the Tricord Club, which is a group of 5 to 7 year old children with physical mobility issues. I'm going to put something together for them. It'll be on April 17th at 2 to 4 p.m. in Metairie. If anybody wants to join me, that'd be great. So let me know. It'd be fun for a couple of us to go do that. And a couple of individuals have tagged me, interested in the club. I think I saw one of them online tonight. And that's all I have tonight. Thanks.
Okay, thanks, Jeff.
I
Yep.
might be able to help with the Metairie thing.
Okay, I'll tag you with the info. Thanks,
Okay.
Mike.
Hey, Philip, can you hear Stephen Harrison?
Yes.
Okay. Yeah, I'm the guy with the excavator, and I've been using it this week. It's working really good.
Mhm.
Still struggling with how to get it there. But I'll keep looking at that as well, and not give up hope. I've got a trailer, but kind of like your connection, Jeff. It's just right there at that limit, that magical limit, 16,000 pounds plus a 5,000 pound trailer is right at the limit of my truck as well. So we're still trying to figure that out.
Yeah, I think
And,
there was also a question of whether we could get over the bridge as well, going up there.
Which bridge is that?
I think it's the one on the dirt road.
Yeah, I looked at that when I went up there last month. There's no load limit signs on it, which really surprised me, to be honest with you.
Okay.
It's a concrete construction, doesn't look to be very old. I mean, maybe some of the other members know some history on that. Maybe it was replaced at some point, but there's no load limit signs on it.
Okay.
Hey, Jeff, you know if there's a turnaround on that road any place, that we can, move a pretty big trailer and get going the other direction, just so we can get out?
It's pretty tight. I got to tell you that. You'd probably have to get into our site and swing around in our opening, right, in our open field. I don't see any other way, to be honest with you.
Hey, Steve, it's Jamie. If you take Daniels Road and you follow it around, when you reach the end of the gravel, you turn left. You follow that road around, you turn right, it brings you out on Highway 16. So there is a way around the bridge. You just have to come off of Highway 16.
Okay, because I'm just kind of afraid if I was able to get my truck in the trailer back there, will I be able to turn it around and or get out of there?
Right.
And because I don't know.
Yeah, he'd have to loop around, right? That's what you're saying, Jamie. I
Yep.
was thinking of a turnaround. I don't think there's room enough to turn around anything long, but yeah, you could loop around like Jamie's saying.
Okay, and additionally, I've been talking with a friend of mine that runs a youth program out of St. Stanislaus, and he's got a group of kids, and they're doing some hunting activities and an overnight camping trip. And I was just talking to him about maybe, because he asked me about throwing in an astronomy event. This would be probably in Mississippi somewhere, and I might be looking for, a person or two with a scope to come help me with that. And that would probably be in a May time frame or something.
Okay. Awesome. So we got a couple potential, or at least one confirmed outreach and potentially another one.
Steve, the one in Mississippi is that the Boy Scout camp?
No, this is some sort of youth program out of St. Stanislaus. And
Oh, okay.
I guess it's supposed to serve, some urban type people that don't really get a chance to go out and observe nature. And they're taking them out on a camping trip. And I was approached about, hey, during this camping trip, could we maybe have a short astronomy, session, the evening of the trip. There's a couple guys up here that I know that have thousands of acres of land. One's got about 5,000 acres of land, and he's got big areas where we could set up with a pavilion close by. It'd be a pretty comfortable environment, but that would be basically in northern Hancock County.
You got a date or around a date?
No, I'm still working on that. I'll definitely notify as soon as I can.
All right. I may be available, but again, it depends on your date.
Sure. Well, I told the guy, I said, well, if it's a full moon night, we'll look at the moon. If it's a new moon night,
There you go.
we'll look at whatever we can. So, all right, thanks, guys.
Okay, awesome. Okay, this next slide is just a reminder that we are, there was one person who said they could send some photos, so we're going to be looking at that, and basically future presenters, as we talked about earlier, we're looking for them always. We're trying to fill up the schedule for this year. I don't know why it keeps jumping around. Okay, so the next in-town star party is going to be April 16th. There was basically a request to shift it by a week. So this month's will be when the moon is out. The argument basically was that, yeah, sorry, I didn't update this here. But basically, yeah, it's going to be when the moon is going to be out. I think it'll be about half. And so people can do some basically lunar astronomy as well as look at any objects. Typically, the objects that we can see in the city are star clusters, any planets that are up, because currently there are no planets up. So really, there's just a few star clusters to see, and there's Orion Nebula. This will give people the opportunity to look at also the moon, which is nice to look at and talk about and look at the different craters. So we're going to do that this month. We haven't had a lot of, yeah, I didn't update this statement here. Sorry, I apologize. But we only had 3 people basically this last month. That was 2 weeks ago. And yeah, so we're going to continue to do it as long as people are coming out. I guess if we continue to have the low turnout, we'll have to see if we continue to keep doing it. But the location has worked out well. This time we moved a little bit more towards the center of the park. So we moved a bit away from the lights, and it worked out quite nicely. As long as it's dry, that part of the field is quite nice to set up in. Okay. So before we get to our topic, I did say basically in the, if you guys read the PS Times, that this time of year is the time of year where people try to do this event called the Messier Marathon. So people try to, in one night, take a look at as many of the Messier objects as they can. And I don't know if anybody in the club was able to do that. Did anyone attempt the Messier Marathon this year? So I figured we could try to do it here in the meeting tonight. So I have been through that site that I presented in January. I've been slowly, capturing different photos, and I got quite a few. I don't know the exact number I have, but I have quite a few of the Messier objects. So I don't have all of them. So I didn't, of course, didn't do them in one night, and I don't have every single one of them. But this is our kind of our shot to take a look at a lot of them. So I'm going to go through them kind of quick. Feel free to stop me at some point if people want to talk about a particular one. But here we go. So M1, of course, is the Crab Nebula. You guys actually have seen this one before. I showed it in January. This is M3. It's a globular cluster. Then M4, another globular cluster. And this is M5, another globular. And then we jump to M9. I try to get the ones in between, but the weather didn't cooperate. The next one is called the Mir Ball Star Cluster. It's M10. And then we get to M11. A lot of people look at this one. It's quite bright. It's the Wild Duck Cluster. It almost looks like a globular, but it's a little spread out. And then this is the most famous one that we look at in the Northern Hemisphere. It's by far the brightest and the biggest, and it's in Hercules. It's called the Great Hercules Cluster. And then we got M14, another globular cluster, and then M19. So we jump. I didn't get the ones in between, unfortunately. And then we start getting into some of the nebulas. So this is M20. This is the Trifid Nebula. There's actually some of the ones I missed. There are nebula. So I think 17 is the what is that one? That's maybe the Lagoon Nebula, and I think one of is it M8, or maybe M8's the Lagoon, and then M17 might be the Eagle Nebula. But there's a couple nebula, really bright nebula in the sky that I missed. I didn't get a picture of. And here's M23. This is an open cluster. M25, another open cluster. And M26, another open cluster. And this is one a lot of people look at. This is a very nice object to see, even with if you have dark skies, even with a smaller telescope, you can at least see this. It looks like a smudge in the sky. It's a Dumbbell Nebula. And then this is the only galaxy you can see with your naked eye in the sky. So if you look up on a very dark sky, you can see the haze of the Andromeda Galaxy. And this is M35. It's another open cluster. And this is M36, M38, and this is M41. This is Aristotle's star cluster. You see the sky was a little bit cloudy when this photo was taken. And of course, M42, everyone's favorite. It's pretty amazing nebula. And then this is one you can see now up in the sky. It's the Beehive cluster. If you come out to the star party here in 3 weeks, you'll be able to possibly see this depending on where the moon is. And the next one is on M45. So this is the Pleiades. The Pleiades is also visible in the night sky, and it's visible with the naked eye. It's pretty impressive. And M47, another open cluster. M48, open cluster. So we start getting to some of the galaxies. This is an elliptical galaxy, M49. Then we get to the Whirlpool galaxy. This is a very beautiful object, especially with astrophotography. You can get a lot of color and detail. Then there's M53, globular cluster. M58, this is kind of an irregular galaxy. And then M61 is called Orionis galaxy. I guess might be the person who discovered it. And then M63 is a very nice object because it kind of looks like a sunflower. They call it the sunflower galaxy. And then M64 is a black eye galaxy, and you can see kind of in the center, it's like part of it is darker. That's why they call it the black eye galaxy. And then we got the M66, which is a Leo triplets galaxy. And these are also very nice to see with kind of a moderately sized telescope. And we got some more globular clusters. This is M68. M71 is a reflection nebula. And M74 is called the Grand Design Galaxy, and it's a spiral galaxy. M78 is another reflection nebula. M82, maybe I got these backwards. Yeah. So M82 is a cigar galaxy. And the one I skipped, I got a reverse, and M81. These are kind of actually very close to each other in the sky. You can see them usually through the same eyepiece. M83 is what they call the Southern Pinwheel Galaxy. It's a photo of it here. M85 is a lenticular galaxy. M90 is another spiral galaxy. Same thing with M91. This one's quite faint. M97 is also a very nice one to see. I think you can see it even with like say a 4-inch refractor. You can, in a really dark skies, you can get a glimpse of it. Yeah, but it's quite small. M98 spiral galaxy, and then M99 another spiral galaxy, and then M100. This one's kind of nice. You can see a couple other galaxies within the photo. And then M101 is the Northern Pinwheel Galaxy, but it's the one everyone refers to as the Pinwheel Galaxy. I showed this before. This is M104, the Sombrero Galaxy, and then M106 is the Spiral Galaxy. That's it. I didn't capture them all, but at least it gives you a flavor of the Messier objects up in the sky.
Nice.
Okay.
Mhm.
So now I'm going to turn it over to our presenter. So our presenter this month is Philip Richardson. He's going to talk about Mars and the Jezero crater and what the Perseverance rover will likely be looking for during its surveys in the coming years. So I will stop sharing.
Okay, you can hear me?
Yes, we can.
Okay, good. All right, let me try to do this share screen thing here. Let's get this up.
Joe, you might have to enable
Oh,
the
you
sharing.
gotta, it's saying disable. Okay, here we go. All right. All right, here we go. Good. Okay, so everybody can see this okay? Looks good?
Yep,
Absolutely.
got it.
All right, great. All right, so we'll get going here. I'm not sure how many people were here in the club around 2017, 2018. I kind of did a similar talk. Obviously, it had nothing to do with Perseverance or Jezreel Crater. It was on biosignatures and some things that were seen by the Spirit Rover and Curiosity. So this is obviously Perseverance. You know, it just got there, just landed. So there's really nothing directly to present from the rover itself. So this is going to be just kind of a look at what they're thinking about, what they're, you know, might be trying to target in the crater itself based on orbital data, geologic mapping, and just kind of how they designed the rover to look for these types of things. So we'll go ahead and get started. So right here, this is, I'm first going to do just kind of like an overview of some things, of some concepts to kind of just put everything into place, and then we'll go ahead and then get to more on Jezreel Crater and biosignatures. So this right here just kind of tells us kind of where we are now. So this is kind of just an overview of NASA's strategy for Mars exploration. So I kind of look at it as kind of two phases. You have this sort of first phase, which began with the Mariner program back in the 60s, and it kind of culminated with the Viking landers in 75 and 76. And so this was kind of, at least looking at it, you know, the way I look at it is sort of the point that they reached, you know, is there life on Mars? You know, back when you go back in the 50s and the 60s, or even going back before that, with Lowell looking at Mars canals and all this other stuff. So this was kind of the end point of sort of that movement. And Viking actually had some experiments on the landers to test the soil to look for some sort of, you know, microbes or some sort of life in the soil. And one of these experiments actually came up positive, this thing they call the label release experiment, which is still talked about today. People still go back and look at that and try to explain how you got a positive result on this and you didn't get anything on these other things. So this thing is still kind of generates a little bit of controversy. So after this, NASA kind of started looking at it a little bit different. You know, how we're going to do sort of a more methodical exploration program, sort of going back, you know, start looking at the geology, start building up a geologic history for Mars, understanding where water might have existed, at what time periods. So to do that, you need basically these robot field geologists to go out and start looking at things. So you need to be mobile. So you need rovers. And also you're going to get a new class of orbiters to start looking at these sites in more detail, figuring out where you want to go, you know, what's there, what you want to target. So this starts up sort of the second phase, Mars Pathfinder, Spirit, Opportunity, Curiosity, and then all these orbiters that they put on there to start looking at Mars in a more comprehensive manner. So this is where you get this follow the water. So basically looking for evidence of water. These other ones really kind of begin here, over here by Mars 2020, explore habitability, seek signs of life, and prepare for some type of a human exploration program. So this is kind of where we are. And as far as I know, future proposals, I don't know of anything that is beyond this, except for the sample return. But that's not really a program yet. And we'll talk about that later. So that, Mars 2020 is going to collect cores and they're going to do a sample return mission. But as far as I know, nothing is concrete on the books or funded or anything like that. So this is kind of where we are right now. Okay, so this is just going to be a quick review of geologic time, looking at Mars. When you start talking about Perseverance, Jezero Crater, water, you're going to hear this term Noachian. Everything's referred to as, Noachian this, Noachian that, that kind of thing. And this is really the time period that is kind of most important when you start looking for these things. When you start looking for biosignatures, you need to look for climate habitats that are conducive to some form of microbial life. And the period where this type of conditions exist is basically way back here. So, so from about, say, 4.2 to maybe around, 3.6 or so, somewhere up in here is sort of the time frame that you're looking for. So these are the terrains that they're targeting when they start looking for these biosignature things. And there's a lot of unknowns in dealing with this. They have this thing called the faint young sun problem, where the solar luminosity was about 70% of present day values. What type of atmosphere, what was the composition, how dense it was, the magnetic field on the planet. This was lost at some time in the past. Volcanic activity up in here. This is this Tharsis volcanic plateau. This is where those big shield volcanoes were occurring. Syrtis Major is another big shield volcano. And then you also start dealing with these really large impacts. These are these large impact basins on Mars. And then you hear this term, late heavy bombardment. So the thought is, early on, obviously you have these really large impacts, planet-sized type bodies, but then it drops off fairly quickly, but then you have this spike up in this period right here. So this kind of limits how far back you would think some type of living thing could be on a planet if it's getting hit by these big impact bodies. And we get all this basically looking at the moon, looking at lunar samples. So the idea is all the terrestrial planets went through this: Mars, Earth, the moon. Obviously on Earth, we don't see it. We don't see the surface effects or cratering, but we see it on the moon and Mars. And on the moon, we actually have dates. So all these dates with these large impact basins cluster up in this range right here. So there's still debate about whether this is a real thing or how bad it was, what was going on. So if it's not as bad or not as catastrophic to the surface, you can kind of extend this green area a little bit further to the left. But this is still kind of things that are unknown. And Mars is also thought to have gone through a just like Earth got hit by like a Mars type body. Mars was thought to get hit by like a Ceres type body, and that's how we get that northern basin. And we'll see that a little bit later too. So up any further back, you start getting, inhospitable type conditions. The crust is too hot, possibly magma on the surface. So say around 4.2 or so is kind of, how far you can go back due to this type of stuff. But going back here, this is the other reason why this time frame is important. It's this active hydrological cycle. Basically, we have flowing water. We have surface water. We have exchange from the surface to the atmosphere and precipitation. So, this is crucial in having this type of a system going on. And it's up in here, so essentially around 4 to 3.6 or so, when you have these things called valley networks. And this is what you look for when you're looking to send type of a spacecraft or rover to look for things on the surface. You want to see moving water. You want to see somewhere the water existed and was there for a significant amount of time. Beyond this, things start to change on Mars. You start losing the atmosphere, the surface water starts going away, you start getting increasing radiation at the surface, Mars gets much colder, less volcanism. So anywhere getting close to say 3 billion years ago, you're kind of just out of the range to look for anything. So, and some other things are what they call aqueous mineralogy. We'll talk about that a little bit later too. This is when the crust or the surface crust on Mars, which is mainly basalt, was altered to these clay minerals. So this is another big indicator. And you can detect all this from orbit. So this is another way to target a location. So, but essentially when you get close to 3 billion years ago, you're pretty much out of the time period when you would expect to even look for any kind of sort of microbial life. Basically from here to the present, Mars pretty much is thought to look like it does now. It's pretty much, kind of a dead, I'm not going to say dead, but, it's kind of did its thing. Okay, so this is one of the big questions is what type of climate they had back then. And probably what you were used to hearing is just warm and wet. Mars was warm and wet way back then, kind of like Earth is now. Thinking now is probably not, or at least not for a very significant amount of time. You start looking at more colder type climates, subpolar Iceland, or something that's really cold and dry, like the Antarctic. So that's where this comes now, this icy highlands hypothesis. So this is kind of what the thinking is that you had something that was more like this, where you had these colder highlands in the south. You get these periodic melting episodes, either due to impacts or volcanism. You can get water flowing. This is all still kind of, just a big unknown. And the reason is you still got these problems that nobody really understands yet. You still have the problem with the faint young sun, low solar luminosity, you get less energy. And then the question is, how much of a greenhouse effect you have in the atmosphere? What is the composition? Carbon dioxide, how much methane do you have? So how much of these greenhouse gases, how much of an effect can you get to where you got conditions that can have water on the surface? So this is sort of the kind of like the end members, cold and wet, warm and wet, cold and relatively dry, or warm and dry. So kind of going between these two right here, you have something that's more like a colder type of climate that, and you have sort of these turbations of volcanoes or impacts that kind of shifts things into a more of a warmer climate. So again, this is still something that just hasn't been figured out yet. Okay, so this is kind of where we at. 3.8 billion years ago, Earth and Mars. So you can say, you know, Mars was kind of like Earth back then. Heavily cratered surfaces, water, oceans, these crater lakes. Mars is going to be a little bit colder, so that's why you're starting to see they got kind of this snow in the highlands. So you got more of a colder climate here versus what you would see on Earth. And really, you probably, at this time, Earth, you probably won't even see you might even see the surface, because I think there's this methane haze that kind of enveloped the planet. So, you know, this is, you know, just kind of what you would see if, you know, if you didn't have that atmosphere. But the important thing is to, you know, when you start looking at Mars and Earth, on Earth, this terrain's gone. You know, we don't have this anymore. This you know, all these craters, basically this whole crust has been squeezed, heated up, subducted, recycled. We can't find evidence of this anymore. On Mars, you can. You know, this type of terrain still exists, and that's kind of what makes Mars important. And that you can kind of go there and kind of go back and see what we had over here on Earth. So on Earth, at some point, we don't know how or when, plate tectonics started getting activated, and you know, still going to today. So things have just gotten, you know, metamorphosed and basically wiped out. Okay, so this is some of the evidence that we have for water. This is all looking at it from orbit. Most important for what we're talking about are these valley networks. These are sort of these dendritic patterns. And basically this is from surface waters. Some sort of precipitation, rain or snow, but some sort of precipitation of water on the surface, generating these networks from high areas to low areas, and the low areas are craters, you know, for the most part. So you'll get these networks that basically will, you know, breach a side of a crater, fill it up, and then breach the other side and empty out. So you have these inlet valleys and these outlet valleys. And that's basically, when you look like Jezero crater, that's what this is. So these types of terrains are old. You know, these are the older types of terrains. So this is the what they call Noachian valley networks. And then you also see these mineralogies from orbit. These are alterations of the basalt crust by water, and you get these clay minerals. And again, you can map these things from orbit. And really, the only way you can get these types of things is just some sort of water activity. And so these two are probably the most important for the time frame that we're looking at. A little bit later on, you get these things called outflow channels, and these are just these huge, massive releases of groundwater. It's either permafrost, an aquifer, some sort of mix between the two. You get some type of a heating event like an impact or some type of magma event in the subsurface, and you just get these big, huge outbursts of these groundwaters. And this is actually, I think, the largest one. And it's just huge amounts of water that's heading out. And you just get all these features that you can just tell, what the flow pattern is. But these are a little bit later. And we also see evidence that they had an ocean. So this is in the northern lowlands, the Borealis Basin, which was thought to be created by this big series type impact. And so you'll get these sort of paleo shorelines that show up. And when you have an ocean, you can also have these tsunami events. So this is where they were kind of able to look at and say, these two shoreline stands were generated by tsunamis from impacts in the ocean. So big asteroid hits the ocean, generates this tsunami. So you get these sort of this run up and then this draw back down. And what was kind of interesting about this is that they had two events that they could distinguish. The older one was more fluid, more liquid, but the younger one looked like it was more ice dominated. So anyway, plenty of evidence for water. And this is what we see from rovers. This is from Curiosity at Gale Crater, stream bed conglomerates. This is like one of the first things that they saw after they landed, were these outcrops of these conglomerates. And just comparing them to Earth, it's, this is pretty much, tells you had some sort of fluvial activity running through here, generating these conglomerates. Okay, so plenty of evidence for water. Big question is, where did it go? We don't see it now. Obviously, we don't, we can't see it. So where is it? And the sort of the running theory was that it got lost to space. Now what the thought is that it's actually still on Mars. It's just been incorporated into the crust. So this is what they call a hydrated crust. But it's locked up in these minerals. It's not a free flowing thing. It's locked up in these alteration minerals that we just looked at. So this is kind of sort of the water budget. You got this initial water. I'm guessing from the planet formation, some additional being output from the volcanoes. Most of it's going back into the crust, into these hydrated minerals, where it's getting locked in. Some's getting lost to space. Around 3 billion years ago, water budget's much less. Still getting maybe a little bit from volcanoes, losing to space, and then a portion of it's locked up in these polar caps. And so, anyway, this is kind of the water story about, we had lots of water. We kind of know that, what happened to it. Okay, so now we got all this water, life forms. You got water. Okay, you got the possibility of having some type of a life form. Where do you look? And again, you come back. Well, where do we find it here? And so these are some of the environments that you would look for on Mars that are analogous to what we had here on Earth. These alluvial fans, they call these things deltaic lacustrine fans. So basically this is alluvial fans that go into water and get deposited in the water. This is kind of similar to what they think was at Gale Crater. So you had this kind of standing small lake that over time would dry out. It may fluctuate, you know, in level, and you're getting these sediments that are getting deposited as an alluvial fan, and they have plenty of evidence for this in a Gale crater. The other is hot springs and geysers. This is a real big one. Hot springs have these runoff channels with all these microbes that live in it. If you've ever been to Yellowstone, you've seen these things. All these colors that are around geysers, sort of these what they call thermophiles that live in these types of environments. You know, geysers, and this little picture down here to the lower left. This is from the Spirit rover, where toward the end of its lifespan or its traverse, one of the wheels got stuck. I don't know if you remember that. The wheel got stuck, and basically it was dragging it along. So it started digging these trenches, and it trenched up all of this white-looking material, which they figured out was actually a pure silica type material, and that's what this center is basically called. These hot springs material. So this is something that they found, and we'll talk a little bit more about this later. So another place you might look are these seafloor hydrothermal vents on Earth. When we think about these things, we think about mid-ocean ridges. Mars doesn't have mid-ocean ridges. It never did. Mars is what they call a one-plate world. It just never had that type of activity. But when you had these impact craters, you could start getting something that's similar. So these big impacts generate a lot of heat from the impact itself. You also can generate these deep fractures down into the crust, tap into some hotter crustal material or magma, and you'll start getting these circulation systems, and very similar to what you would see at like a mid-ocean ridge. So the kind of things we're talking about, looking for, it's bacteria, you know, microbes, things like stromatolites, microbial mats. Probably in the worst case scenario, just be something like this biofilm, where you just basically just got some carbon left over. But the key criteria that we're looking for is, you know, habitability. You got water. What's the pH? You can't have it too acidic, too alkaline. The salinity. How long was it there? Are you getting nutrients? And the potential to basically create a fossil, something you can find later on. Rapid burial, a low energy type environment. You don't want things getting torn up, tossed around, and then some type of mineralization, something to preserve it. So these are the things that you're looking for. Okay, so Mars 2020, where to go? So how did they decide to go to where they are, to Jezero Crater? So they had this site selection process. And then, so going from, say, Curiosity to Mars 2020, less geology, more astrobiology. So the focus kind of shifted now back to, okay, now we're gonna go back and start looking for some type of a, you know, life form. And so they had these workshops or committees, or I'm sorry, conferences, starting 2014, so one 2014, 2015, 2017, 2018, basically narrowing down the list of options. So starting in 2014, you had 64 proposals or candidates. So basically the first selection criteria was, number one, you got to meet all these engineering requirements. So basically the engineering of the rover, what is the landing requirements, what type of terrain you're going to be on, and how far you have to drive to do all these other things, these mission science objectives. And again, astrobiology, what type of environment, what type of preservation potential that you have. The other thing is this: assemble a sample cache, including igneous rocks. These are the drill cores. So, you know, how diverse of a rock assemblage can you get from where you're going? And the important thing to include igneous rocks is to get age dates. You know, igneous rocks, you know, we can get age dates on those. So basically, you want to constrain the age at what you're looking at when you're getting your samples. You need something that you can date. And then consistent with the technology elements, this is the helicopter, and then the Moxie, which is a CO2 to oxygen experiment that's on the Rover. And so the goal with the samples is to get 20 drill cores in 2 years. So that goes back to the driving distance. You know, how far do you got to drive to get 20 drill cores in 2 years? Okay, so going from 2014, for the 2015 workshop, it gets narrowed down to 21 candidates. You get a little more specific about what they're looking for. So this is the selection criteria up here at the top. Again, habitable environments, biosignatures, sample return. And then we give them the scores, and you can see Jezero Crater is pretty much #1 on just about everything. Then you go to Columbia Hills. This is back where Spirit was. And this Northeast Syrtis, that's actually right in the vicinity of Jezero Crater, and then some of these other areas. So they narrowed down to 8 for 2017. Columbia Hills, Jezero Crater, Northeast Syrtis, Nili Fosse, Holden Crater, Eberswald, Marth Vallis, and the Southwest Milos Basin. And I just had a couple things here I put about how they eliminated some of these locations, like Holden, too much driving. You just have to drive too much to get to where you wanted to collect samples. And it was also too far south. This is something I actually kind of found interesting. The plan is to put the cores in specific locations on the ground, and they didn't want them sitting out in areas that were getting basically too much sun exposure. This Eberswald, the delta, it's a crater with a delta in it, but the dating is just too young. Around 3 billion years old. It was just too far out, and it was also too far south. So anyway, we get to the 4th workshop, which is 2018. So we're left with Columbia Hills, our Gusev Crater, Jezero Crater, and this Northeast Syrtis. And the interesting thing is that Columbia Hills actually scored low. They actually eliminated it in the 3rd round of the voting. But this site selection committee, I guess, overruled everybody and put it back in. and there's a reason for that, and we're going to talk about that in a minute. And if you've got any comments or questions, go ahead. I mean, because I'm just going to keep rambling on. But you know, if you got anything you want to ask about. All right, so these are the final 3. Jezero, Northeast Syrtis, and Columbia Hills. And this is basically, you know, what they found that, you know, was what they were looking for. All right. And they also added this 4th place in called Midway, which is midway between Jezero and this Northeast Syrtis. So it kind of put that in here to, since they're fairly close, they kind of looked a little bit more and said, okay, well, we got this area that's similar to this northeast Syrtis. So we're going to go ahead and stick that in there, and then we'll look at that more later too. All right, so this is the final ranking. Again, Jezero Crater is up there. In situ science, the returnable core or returnable cache science, and then how much confidence do you have that you can deliver on the other two. And so this is for the prime mission and then the extended mission. So basically this eliminated Columbia Hills as being the final landing place. All right, so we're gonna go back, just look at Columbia Hills real quick, because this is where Spirit was, and this is looking at why did they put it back into the final round. So impact crater, possibly with this eroded delta, big lava plain. So it's kind of like, well, what made this one, what made, Spirit already went here, why would you send something else back? And so this is where Spirit landed and traversed across this big lava plain and came to this area called Columbia Hills, which they think is probably the central peak that was generated from the impact event. And it ended up in this place called Home Plate, which is a volcanic feature. So this is this home plate feature, some type of volcanic clastic deposit. But what they found interesting was what was around it. They found these outcrops of this silica, and from the wheel dragon, that's how they kind of discovered it. And this here is kind of what made everything much more interesting. So the top part is Mars, the bottom row is this geyser field in Chile. So these features that they see, these are silica nodules, and they have sort of this cauliflower looking type appearance. But if you do sort of a direct comparison to this geyser field in Chile, they look awfully alike. So essentially, this is really the only potential biosignature that has been seen. And this is kind of the reason why they stuck it back into the ranking. Anyway, this was interesting right here. So and again, this is kind of things you're going to look for. Something that looks very similar to what we have here on Earth. This stuff on the bottom, this is all because these are basically stromatolites. This is all algae type growths down here that produce this type of morphology. And it looks awfully close to what they saw there on Mars. So, all right, moving on. So we got Jezero Crater. This is kind of the vicinity. We have this large impact basin right here that sits on the edge of, and it's the impact around 3.8 to 4 billion years. Jezero Crater, they kind of date at least 3.8 billion years. And then you have this broad, low relief shield volcano down to the southwest, Syrtis Major. And if you're a visual observer of Mars, this is like a really dark feature, very prominent. And then you have the real light feature of the basin. So this is something you can actually visually observe, this big shield volcano area. All right, so a closer look. Jezero Crater. The most prominent feature is this western delta, and they also think they have another delta to the north. They call it the northern delta. It's much more degraded, eroded. So they're not really sure if it's a delta that formed from this northern inlet valley, or it's just part of the western delta. But the Western Delta is real clear. This inlet valley to the west breached the side and produced this delta. Over here to the upper left, this is a map of the watersheds that fed these two deltas that filled up into the crater. So basically, water and sediment that was caught up here traveled down to the southeast and into the crater, and the crater basically filled up with water until it hit a certain level and then breached out the eastern side, and that's what you see over here, this eastern breach. And at the bottom is a artist's rendition of kind of what it would look like. So you have this big crater lake with the western inlet valley, and then this outlet valley over here to the east. And this is kind of neat. So this is over here to the lower left. These are the landing ellipses for the different landers and rovers. So Mars Pathfinder, Phoenix, Curiosity, and then Mars Perseverance. And hopefully, if you've watched some of the videos that they have online of the landing, because it's really cool. And the thing that Perseverance had was this onboard navigation system, basically a terrain mapping system that it could look out at where it is, match it up to onboard basically terrain map, figure out where it is, and adjust where it wants to go. And this is basically what allows them to target a feature like this. Curiosity maybe could have done it, but it would have had to land much further away, and it's too far to drive. Perseverance is about 2 kilometers from that delta. So it's really, really pretty amazing with how they've been able to shrink this down. All right, so this is a geologic map. And obviously this is all generated from orbital data. But this is a US geologic map. You have the landing ellipse, and the dark blue is the western delta. The light blue is the northern. Have the crater rim. The red line, the purple line and the red line, these are possible routes that the rover may take. But I don't think anything's been decided yet. This Belva crater is about 1 kilometer in diameter. So the rover is about 2 kilometers from the fan. Anyway, and the A prime, that's a cross section, which is this right here. So again, I don't know how much they know of this. I mean, this is all generated just from what they can map from orbit. So this is sort of just kind of the relative position or layering of the different units. And you got the crater rim, and then the alluvial fan that comes out into the crater. All right, so this is a little bit closer look at the delta unit. And going back to the geologic map, obviously the delta was considerably larger, and it's been eroded back. But what you see are these lobe type features, these dotted blue lines. These are individual lobes that came out at different times. They cross cut each other, so you can kind of tell which one came before the other one. And then you'll also see this thing, they call these inverted channels. So these are actually channels where the water flowed, and at the time when water was there, they were lower. So they were lower in topography than the surrounding area, but because of erosion, you got harder materials in these channels. They now stick up. So they call it inverted because it should be lower, but it's higher. Okay, so this is a profile, sort of a 3D profile view of the crater. Again, you can just inlet valley with the delta. Some of these units, you can tell they have different sort of a surface expression. And then sort of these lobes that are coming out from the delta. And this is kind of neat right here. So this is the landing area for the rover. So these two craters are these two craters right here. That red dot is where the rover is located. So basically, just in this area, they got the parachute and the back shell, the descent stage. Is the rover, and over here is the I can't see heat shield. Sorry. So basically, all this stuff is within driving distance. So I'm kind of curious if they're going to try and go take a look, you know, at any of this. You know, just kind of it'd be kind of neat to see like the descent stage. I think to kind of see what happened to that thing after it hit the surface, or use the helicopter. You know, maybe. But anyway. This is kind of neat because everything's all right in that area. Okay, so this is a panorama. This is like this is basically the first panorama that I think they put out to the public, this is a big image. It's got a lot of detail. So these are crops that I kind of took out and. Kind of see, you know, what I can identify in the image. So first thing you got are these light colored areas. These are the blast zones from the descent stage rockets blowing out the material. This sort of low ridge right here, that's the delta. These high sort of hill looking areas in the distance, the crater rims. And then you got these kind of little knobs over here towards the northeast. These are those remnants. Okay, so this is kind of looking to the west. So over here, if you look at the geologic map, the black arrow kind of shows the general direction that you're looking. And so looking from the rover, you have, this is all delta material right here. And over here is this delta remnant. So this is kind of this blue area right here. So the arrows kind of correspond what you're looking at in that 3D profile view. So the blue arrow are these prominent delta features right here. The red arrow is looking at this remnant, and then this kind of gold color arrows looking kind of through this kind of valley area at one of these lobes. And kind of same thing here, just looking towards the north, crater rim in the distance, much closer to this delta. You can see the layering in the kind of ridge feature right here. So that's the blue arrow. This kind of gold yellow arrows kind of looking past it at this more distant, these two lobes right here. And then this red arrow, you're looking past this kind of remnant feature right here into this lobe that's way in the distance. And so the black arrow kind of shows where you're looking. So this right here, this kind of little hill that's out in the middle by itself. That's that remnant that's right there. And this is going to the northeast. You got these three remnant features from the delta. So at one time the delta extended much further. This area in the foreground is the blast area from the rockets, and it's hard to tell. I mean, it may have like a little kind of uplifted area right here. That's this little small crater. That's pretty close. All right, so what did Jezreel crater look like? There's a lot of interest in this lake in Turkey. it's a crater lake, but it's a volcanic crater, not an impact crater. It's got these alluvial fans that enter into the lake. And it's also got what they call these things microbolites. And essentially these are just microbial mounds, bacterial mounds. So it's kind of a mix of different types of sediments. These darker, this is from the surrounding rock, or probably like basalt. And then these light color material is carbonates. And all this carbonate material is from just erosion of these microbolites, which are formed out of this hydromagnesite. So you got calcite, you got magnesite, just different types of carbonates, these terrace features. So this is all carbonate material. And this is kind of what these mounds look like. You have these underground springs or seeps, and then you got this sort of layering. This is in these deltas that extend out into the water. So you're kind of looking at this as kind of sort of a Earth case study as to possibly maybe what the crater was like. And what they really are interested in are these things called these marginal carbonates. So these are sort of these carbonates that are along the edge of the crater. So that it would be this bright blue, dark, or I should say dark blue feature over here. And so there's questions about, what is the origin of this material? Did it form in the lake? Or was it brought in from the surrounding area? So that's kind of the questions that still need to be answered. But it has kind of this rubbly appearance. So it's very distinctive. And some other evidence that's possibly was formed in the lake itself. It kind of has this restricted elevation range. And the elevation range is kind of between what they call the high stand. So this is how high the water got in the crater before it breached to the east and went down. So it's kind of in between these two elevation levels. And this sort of represents what the shoreline would have been before the crater breached and the water went out. So let my cat out. All right. So anyway, this is kind of these are things they were looking at when they were trying to figure out where to go. All right. So we look at the rover itself. As far as like biosignatures are concerned, the two main instruments are, I guess I'd say three, is what they call Sherlock, Watson, and Pixel. These three kind of work together, and they form a sort of a composite image of whatever they're looking at. So you're going to get elemental compositions and distributions, and if there's any organic type material that's in the sample that they're looking at. So basically, you're going to get elemental identification, and then you also going to get a mapping of the element distribution and looking for if there's any kind of structure or fabric. And they did a lot of field testing in Australia of this equipment. And basically what they did was take it out and looked at ancient stromatolites, these 3.4 billion year old stromatolites that they have in Australia. It's kind of saying, okay, what can we do with, how will it look if we find something similar, and basically how will this perform? So, and this is, what they got. So looking for the element, not only trying to figure out what the element composition is, but is there any sort of pattern to it? Something that a pattern that the only way you're going to get that is if some sort of bacteria was involved, some type of life form was involved. You're really not going to get it if it was done by with I guess abiotic processes. It's not going to be something that was just geologically generated. So and the other thing is to look for organic material, and then they show kerogen in here. Kerogen is just degraded organic matter. If you ever heard of oil shale, that's what's kerogen is an oil shale. So, all right, so that's what do you call it? Pixel X-ray spectrometer, Sherlock, a UV spectrometer. And then Watson is just a high resolution camera. Okay, so, and of course, the next thing is the core drilling and sample caching. So this is the plan to take drill cores, sample cores, and leave them in sort of a cache depot on the surface, and then later on come pick them up and get them back to Earth and analyze them in the lab here. So the rover has 43 sample tubes, 37 are for actual cores, 5 are for blanks, or basically to see if there's any type of contamination, and then 6 spares. I forget how it can actually hold them, even after it drills it, it can actually hold them in the rover and hang on to them, and then figure out how it's going to, leave them on the ground. So, and then that's kind of what this little thing is, just, figuring out where you're going to go, your region of interest, collect your samples, head back, and put them down on the ground. And all right. So some of the other instruments, it has a ground penetrating radar. It can go about 10 meters into the ground. What is the depth of the regolith, stratigraphy? It's got the weather station, and then the super cam, mass cam, which is kind of an upgraded version of what was on Curiosity. And then Moxie is one of the technology experiments, oxygen from carbon dioxide. So, and of course the helicopter, which they've dropped the protective cover, and I guess it has to go to, it's going to move to where it wants to lower it down and then move away, and then start flying. All right, so sample return. This is the idea for sample return. European space agencies in the blue, NASA's in the orange, tan, or whatever. The idea is that you would, 2026, you would launch the Earth Return Orbiter, or the ERO, and then the Sample Retriever Lander, the SRL. That's ideal. 2027 or 2028 would be the next opportunity to do that. And then, so if you launch in 2026, you'll get samples back in 2031. These later dates, it'll be 2033. So basically, you're looking at a decade or more before anything gets back to Earth. As far as I know, nothing's been funded. I don't know if you have anything really on the drawing board. The other thing, of course, is the cost. Roughly about $4 billion. I don't know if that includes the 1.5 billion euros for the ESA part, or if that's separate. But the this is still something that needs to be figured out. All right, so it's kind of be the last thing is kind of look at sort of mission profile, sort of kind of, you know, what you would do on the ground. So you would look for these regions of interest that you want to go to, and sort of plan it around what your scientific goals are. So like this would be for exploring delta stratigraphy, looking at the layers that are in the delta. So you set up your different waypoints and your regions of interest. And then another one would be looking at the what they call the distal delta and the lake margin. So some of these lake margin deposits. And then of course, taking your drill cores, you're getting a suite of different type of lithologies, different types of samples, and the final would be this, the crater rim, which is basically considered basement rock. So then you go into what's the extended mission. So the primary mission would be like in the red and the green. So the extended mission, kind of like what they're looking at is two choices: head to the north to look at this northern fan, or kind of head more to the west, southwest, into this midway area that was in the proposal. The thing about midway is you get into much older units. You get older pieces of crust, and this was one of the source areas that, so essentially you can kind of look at, okay, we saw what's over here, what can we match up from the source area? Or if you went to the northern fan, you might get into some different types of deposits. So anyway, I think that's about it. This is some things that are on the rover that's kind of fun. This is the COVID plaque that they had on there. This is the plaque with the etched chips. I don't know if did anybody put their name in for this thing. I put my son's name in, and I told him about it, and he wasn't too excited. Once he found out there was like 10 million other people that had their names on it. And then this is the sundial, which is kind of neat. So you got this color calibration, and then sort of the evolution of the solar system. So you got the formation of the solar system, then DNA, bacteria, plants, dinosaurs, people, and rockets. So, and I think that's about it. Yep, that's it for me. So, all right, is there any questions or anything, or?
That was pretty awesome, very informative. Thank you, Philip.
So, any questions?
I have a couple questions. Philip, that was a remarkable brief. I want to say, I wish there was 10 or 20 times more people listening to it. Couple things. Looking at the distributaries, and looks like there's a lot of erosion going on, and obviously some alluvial deposition and stuff like that.
Yes.
You can, because you can kind of, delta areas evolve, as we know down here in Mississippi and Louisiana. But have they put a time frame on how long it took for that this delta area to develop?
That's actually a good question. Actually, I had it in my notes. I thought that was actually on one of the slides, but it didn't
It
say.
probably was. There's a lot of information you just
Yeah,
gave
how
us.
much, is my screen still being shared or?
Yes.
Okay, yeah, so how much time is represented by the delta? Yeah, that's a big question. And they don't really have an answer. You know, is it tens of thousands of years, hundreds of thousands, or millions of years?
Right.
They just don't really have any kind of an answer on that.
And another thing, getting back to the where'd the water go issue. I mean, obviously, it's not one answer. There's several answers there. But I was just thinking about escape velocities. Free hydrogen
Correct,
is
correct,
on,
right,
and hydrogen atoms or Mars' escape velocity is about half that
correct,
of Earth, about 5 kilometers per second.
right.
So it's just gone.
Yeah, and that's you know, Mars is small. You know, it's small. You know, and that's kind of reason why it is what it is. You know, it's a there's just not much activity going on, and then the like I said, the escape velocity for just a lot of these atmospheric gases is low. So it just doesn't take a lot to knock this stuff out. It doesn't take much energy to kick something out, and lose it.
Yeah, and I'm certain that people have calculated, given a specific volume of water, say the surface of the planet, how long would it take for those hydrogen atoms to disassociate and ultimately
Right.
space?
The I think it's kind of what they had come back to was like the sheer volume of water that was thought to have been there was just more than what you can account for. And then looking at how much water is probably held in the crust itself. And so that's when they kind of think now that most of it is actually still encased in the minerals in the crust. It's just still a big open question as to what the atmosphere composition was, how much of an atmosphere you actually had, and what the dynamics were. They just don't have very little constraints on that, because from what you see, in the geology with these these networks, it's hard to reconcile what you see versus what is there. It's kind of like how do you get all of this water activity and have a process like this going on, but hardly with how much atmosphere you need, because you got to hold, you need a thick atmosphere. If you're gonna have surface water, you need a thick atmosphere, otherwise it's gonna boil off, for one. So you need an atmospheric pressure, and then to have liquid flowing water too. You need what's going to get you there. And they still really just haven't figured that out. And so it's just still big open questions. And then things like this. If you're seeing things like this, what is this? How do you get this, something like this? Is it just pure coincidence, or is it real? That's the hard, another, thing too. It's like, you know, how you know, the only way you're going to figure something like this out is to get pieces of it. You know, it's just about the only way, you know, you're going to get, you know, figure something like this out and get pieces of it, you know, and say, okay, you know, yeah, it looks the same, but it happened, it was done by a totally different process than what we have here, you know. So, because here it's microbes, you know, the stuff on the bottom is all that's microbial type activity going on, you know. So did you have that here, you know? So it's you know, and it's going to be, you know, it's, you know, it'd be interesting, you know, if they come across anything, and then again, unfortunately, it'll take a decade or more, you know, to get it back here, you know, because nobody's going to believe you, just, you know, no matter what you see here, you know, unless it's completely obvious, you know, nobody's going to believe it, but, you know, so. Anyway, so have y'all watched the landing videos? Yeah.
We actually watched that during the last meeting. We watched the landing video.
Yeah. Okay. All right. Yeah. And that was amazing. You know, just and then I thought I had a. Okay. All right. Anyway. All right. So.
No, thank you so much. Does anyone have any other questions?
Yeah, I do. Can everybody hear me?
Uh-huh.
Hey, it's my first time on. Thanks for doing this. You had mentioned it previously, but Earth kind of being like Mars at one point, but not anymore. Do you think there are any direct applications that we can learn from any of this stuff for what's happening here on Earth right now?
Well, you mean like the way Mars is now, what Earth will become?
Yeah, or just anything really, not necessarily temporally out into the future, but just in general.
Well, I mean, if you're talking like global warming, greenhouse gases, Mars's atmosphere is just so thin, you know, it's just so you talk more like Venus, you know, which has like a CO2 hothouse. I mean, a couple things that about sort of what Mars is today is kind of what you would think Earth is going to be probably, say, in about 500 million years or so. Because the heat energy that's driving these plates, you know, plate tech, that's going to run out. That's all from radioactive decay occurring down deep in the you know, the mantle and the core. So at some point, that's not going to be enough, and essentially, it's just going to lock up. And I thought last I read was like the estimate was about, say, about 500 million years or so. Not that we have to worry about that, but so essentially, it kind of what Mars is today is kind of what Earth is going to be at some point. You know, it's you know, geologically and most likely biologically dead. You know? So, but again, you know, that's nothing that we have to, you know, and it's going to, you know, lose its atmosphere. The sun's going to get, you know, even more luminous, and you know, so it's kind of it's kind of a window in the past and a window to the future, you know, a vision of the future, you know. So, but anyway, those are things that, you know, you don't need to worry about at night. So, all right. Anything else?
Are there any other questions?
So hopefully we'll have some more to look at in maybe a year or two when they start getting to some places.
Thank you so much, Philip. This was
All right.
I learned like a ton here. Yeah, you far exceeded my expectations. So I really appreciate this.
Yeah, well, I mean, it's I mean, I have a degree in geology, but I'm not a practicing geologist. I mean, I do GIS work for for a living, so I'm not actually like a like I said, a practicing geologist. But kind of like stuff like this, I just kind of like to just keep a little touch, on what's going on. So just for general interest. So okay, well, let me close this out here.
Okay, well,
I'll stop sharing the screen. Let's see.
thank you. Hopefully everyone, I know it's getting kind of late. Hopefully everyone really enjoyed this today, and that will be the end of the meeting for today. Does anybody
right.
have any closing comments they want to make?
Thanks, Phil. Enjoyed it.
All right, thanks, guys. Y'all have a good weekend.
Okay, thanks everyone.
Until next time.
We're going to be signing off here.
All right, thanks a lot, guys.
All right.
All right.
Thank
All
you.
right. See you next time.
Yep. See you next time.
All right. All right. Good night.
Good night.